all are aware, as you all are aware of the RMK group of institutions conducting a weekly generic talk series on the emerging technologies. On behalf of the management, principal, dean, HODs, and faculty members of RMK CET, I warmly welcome our esteemed speaker for today, Dr. M. Babu, Senior Verification Engineer, Chipstone Technologies, Hyderabad, for the generic talk series on Embarking on VLSI Verification Strategies for Success. Welcome, sir.
Thank you. Thank you.
Now, I would request our beloved HOD ma'am to welcome Dr. M. Babu.
Good morning. Respected today's guest speaker, Dr. M. Babu, Senior Verification Engineer, Chipstone Technologies, Hyderabad. Respected HOD of EC, Dr. Gangadharan sir. Respected coordinators, Dr. N.R. Rajinpal and Dr. N.P. Poniji madam. Student participants and dear faculty participants. Good morning to all of you. So today we have joined here as ma'am mentioned, every Sunday. Only once every Sunday we are conducted a generic talk series. So today's topic is very important topic, that is regarding the embarking on VLSI verification strategies for success. It's a very trending topic, I think so. I hope the students may have enjoyed the session. Also, the session will be more informative. On behalf of RMK CET and principal of RMK CET, and on my own behalf, I welcome today's guest, Dr. M. Babu, Senior Verification Engineer, Chipstone Technologies, Hyderabad. Welcome you, sir.
Welcome, sir.
Next, I would like to welcome HOD of EC, Dr. Gangadharan sir, for this session. Welcome, sir. Next, I would like to welcome the coordinators of this today's session, Dr. N.R. Rajinpal and Dr. N.P. Poniji. And my dear student participants and faculty participants, welcome you all. I request all the participants kindly interact with the guest speaker. And at the end of the PPT, you have the query session. So whatever the queries you have, just you make a note of it and clarify your queries at the end of the session. So I hope all of you enjoy the session. Have a good day. Thank you.
Thank you, ma'am. It is my pleasure to introduce our distinguished speaker for today, Dr. M. Babu. Dr. Babu M. graduated with a bachelor's degree in Electronics and Communication Engineering from Anna University in 2009, followed by a master's degree in VLSI Design from Anna University in 2011. He completed his PhD in VLSI Design from Anna University in 2022. In academia front, Dr. Babu M. served as a faculty in reputed Anna University affiliated colleges for more than a decade. Presently, he is a senior verification engineer at Chipstone Technologies Private Limited, Hyderabad, with extensive experience in ASIC IP and SOC verification. His project portfolio includes verifying security IP, MDFI, AHP Arbiter, MIPI, DSI, UCM, and many more. Welcome you, sir.
Thank you. Thank you for the introduction.
Now I hand over the session to Dr. M. Babu.
Let me share my screen. Ma'am, hope my screen is able to.
Yes, sir.
Thank you. Respected principal of the institution, respected HOD sir, HOD ma'am, and faculty members and dear students. Myself, Babu M. Was a pleasant morning and to have this kind of opportunity to meet you all again through this session. And today's topic is on introduction to VLSI verification. Here we will be discussing some brief history of VLSI and as a VLSI engineer, what are all the job roles available in the market, and opportunities available as a verification engineer. And I will be briefing on what are all the trending technologies in VLSI, and I will give some insight on verification strategies and what is the role of a verification engineer in the recent technology projects handled by various companies. And to become a verification engineer, what are all the requirements expected from students? These are all the things we will be covering today. So with this short note, we can get into the topic. So whenever I go for a talk, I will start with this kind of quote. So the history of VLSI. So we may have seen a lot of chips manufactured by Intel. So we already know that the first chip manufactured in 1970s by Intel, IN4004, it was a 4-bit processor. From that, we already know we are in the era of i9 processors. And parallelly, AMD processor also in the market. AMD 7000 series, isn't it? So Golden Moore postulated one law called Moore's law. So based on that, for every 2 years, the number of transistor density inside a chip will get doubled. So according to that, from the beginning, we have SSI technology. It's called small scale integration, where in a single IP package, we will be having 1 to 10 transistor in a single package. Then comes MSI technologies, medium scale integration, where hundreds of transistors are packed in a single chip. Large scale integration, thousands of transistors in a single package. Then there comes very large scale integration. Here we will be packaging millions of transistors in a single package. So now the technology is very drastic and we are moving towards VLSI and GLSI technologies. VLSI stands for ultra large scale integration and GLSI stands for giant large scale integration. So whatever these progresses in the technologies are aimed towards three main goals. So these three main goals are very important, and every engineers in the verification side as well as in the design side, they are mainly focusing on these three aspects. First one is speed. So speed means whenever we are giving input to a chip, how much time it is taking to come out of that chip. So again, we can able to call that latency of the chip or bandwidth of the chip. So whenever we move from one technology to another, so we are mainly concentrating on how we can able to increase the speed. And second one is on area. So simply we can cannot reduce the area of a particular chip. We need to adopt recent technologies and make sure that how we can able to reduce the size of a single transistor so that the entire chip area we can able to ultimately reduce. For example, I can tell you might have seen 1 GB pen drive, 2 GB pen drive, 8 GB pen drive. Currently, we have 1 TB pen drive also available in the market. All are of same size. Integrate as much of transistors we can so that we can able to use more memory transistors in within the available chip area. The third very important point is power dissipation. Because we have both static and dynamic powers constituted in every chip. So power dissipation plays a vital role when we use battery powered devices. So consider our mobile or some vital role in every a specification, a customer comes with a specification to manufacture a product to an for the end user. The first and foremost thing is the work of a silicon on chip architecture. So when a silicon on SoC architect, so he will go through the entire specification, and he can able to decide what are all the components we need to use for that manufacturing that particular product. So as a SoC architect, so he need to plan just like how we are building, creating a building plan, right? In the same way, we will be having a building plan for our chip also. The second important role is VLSI design engineer. Once the architect is ready, the design engineer so and he will be having some mechanism to verify whether the design is as per the architect, which is developed by the architecture developed by the associate architect. The third important role is of VLSI verification engineer. So once the RTL design is ready, is the role of the verification engineer to check whether the functionality, what is intended for that particular chip is as per the requirement or not. If there any bug or if any fault, if there any violation from the design, so that need to be captured by the verification engineer. That again, you need to report back to the designer. Again, designer will work on that feedback and he will release some other new RTL versions. Again, VLSI verification engineer need to verify it and confirm that functionally it is good. Then the next role is on physical design engineer. So he will be completely working on placement and routing, how efficiently the memory blocks as well as other blocks can be placed inside the available area, so that we can able to, when the area is reduced, the um, transactions through the chip also will be faster. And if we have less interconnects between the devices, the blocks, we can able to reduce the power dissipations also. So once the physical design is ready, the next job is of a physical verification engineer. So he will be having some set of rules to check whether the physical layout is matching with the actual schematic or not. It's called layout versus schematic check. And then they will be checking design rules, whether all the design rules are followed for that particular layout or not. So it is called DRC, design rule check. So all these things will be taken care by the physical verification engineer. Then we need to check whether the design is compatible for the hardware or not. So that comes the role of FPGA design engineer. So he will be checking the entire binary code which is developed, generated from the RTL. So he will be dumping inside the FPGA, that is the general board. So before going to the manufacturing foundry, we need to properly check whether the code is compatible for the hardware or not. Then, so along with the digital component, we will be having a lot of analog components also associated with the chip. For example, if it is a PLL, if it is a filter, analog to digital converter, digital to analog converters, all those things will be designed by analog or mixed signal design engineers. Then the role of a DFT engineer come into play. This is completely on the testing side. So the DFT engineer will be, with the help of some tools, he will be creating the complete environment to test the particular chip, and they will verify the quality of the design. And apart from this, we need some engineers for developing the EDA tools. So we have discussed the role of SoC architecture, VLSI design engineer, verification engineer, physical design engineer, FPGA verification engineer, and DFT engineer. All are working with some or other tools to verify whether the design is compatible for the requirement given by the vendor or not, customer or not. So for that, some companies require engineers to develop those EDA tools. Okay. So these are all the jobs available for the VLSI engineers in the market. and opportunities as verification engineer. So here I have noted only a few top companies, those who are recruiting VLSI verification engineers who are verifying their products or some products driven by the customers. For example, Synopsys, Cadence, and Mentor. So you may know that these are all the top vendors of CAD tools. As I mentioned, the EDA tool developer, the ninth point. So those kind of engineers are required by Synopsys, Cadence, Mentor, Graphics, as well as Xilinx for developing the EDA tools. Apart from that, Synopsys, Cadence will recruit verification engineers for functionally verifying the IPs developed by the Synopsys or Cadence. Because whenever, as a verification engineer, if you want to verify a product, we may require some standard libraries that is already created, tested, and functionally proof verified IPs we need to purchase from Synopsys or Cadence in order to save more time in verifying the product which is developed based on the requirement of the customer. So if a particular IP is already verified in one end, so we can able to reuse that so that we no need to develop a particular IP from the scratch, so that we will approach the Synopsys or Cadence. They may have some predefined cell libraries, so we can purchase it from them. For those developing those IPs also, they require VLSI engineers. And apart from that, other top companies in the market which require VLSI engineers are Google, Samsung Semiconductors, Intel, and one of the important project now Google is doing is on autonomous cars like Tesla. And we have opportunities at AMD, Microsoft, Texas Instruments, Qualcomm, Broadcom, NVIDIA, Untethered, Micron. These are all some top companies which requires VLSI role of verification engineers. So we can discuss on some new technologies which is there in which require more VLSI engineers in the market. First one is advanced semiconductor process. So whenever, as we discussed from LSI to GLSI technologies, as the technology progresses, so we need to adopt some processing technologies so that we can able to concentrate main on how to increase the speed, how we can able to reduce the chip area, and how we can able to reduce the power dissipation. So based on that, the now recent technologies are FinFET and GA. So GAA is a gate array, gate all around transistor technology, gate all around transistor technology, and FinFET technologies. And these technologies are used mainly on reducing the chip area as well as power dissipation. So once these two factors are taken care, parallelly the speed of the chip also will increase. The next one is IoT as well as autonomous vehicles. So whenever we are speaking about one home automation, so we need some microcontrollers or processor for controlling the entire household things which is there in a home. So those kind of chips manufacturing, and also for verifying the functionality of those chips. So we require many verification engineers in the market. As I specified, one of the autonomous vehicle manufacturing by Google. So they actually, one of my previous project is on that particular thing. So there in the autonomous vehicle, we had 16 different cameras. The chip what we verify, so which will store and process the images captured by those 16 cameras. So those kind of technologies are supported by VLSI. Then AI. So how an artificial intelligence technology can support VLSI? For example, for reducing the chip area, we used to use placement and routing algorithms. So there we need support of artificial intelligence algorithms which can efficiently place and route. Placement means how efficiently we can able to allocate the space for available IPs within the chip, as well as how we can able to do the interconnection between those blocks. Those can be done by efficient AI algorithms and machine learning, ML, in VLSI. So, we know we have a lot of machine learning algorithm which can predict how the performance of a chip would be and how precisely we can able to take decision on of a particular chip design. All these things are supported by ML. Then 3D integration technology. So actually nowadays there is based on some requirements, we may have stacks of chips. So we will be integrating multiple chips in a single package, so in a 3D structure. So by using 3D integration technology, we can able to efficiently build a chip which can able to consume only less power compared to 2D scaling technology. Then very interesting technology is photonics integration. So here what we will do is all the optical components we will integrate inside the chip itself, so that all the transactions using lasers we can able to control within inside the chip, so that the bandwidth as well as the speed of transactions which is happening inside the chip we can able to improve, as well as by means we can able to reduce the transition latency, and we can able to increase the bandwidth using photonic integration. So next one is quantum computing. So quantum processors. So as a verification engineer, we may need to verify a quantum processor which can support to solve some complex problem with less time. So in this way, we can able to control, we can able to give and some assistance for the entire chip to solve a particular problem within some a fraction of seconds or microsecond time. So those kind of quantum processors we will be using in VLSI technology with the support of quantum computing. And next very important technology is edge computing. So one of my current project is on edge computing, where what we will do is, in normally if you take a server, so the computation of all the elements will be happening outside, and only the storage we will be taken care in the servers. But in using edge computing, in order to improve the speed of computation as well as storage, so we will be having some computation mechanisms inside the core memory itself. So once the data comes, so the computation also will be happening inside the memory, as well as storage also will be happening inside the memory itself. This kind of technology will support in increasing the bandwidth, as well as we can reduce the latency. All the technologies are focusing on the three things what we discussed: speed, area, as well as power dissipation. The next important technology is IP security. So based on the application, so whatever chip we manufacture, there will be some security IP which situated inside the chip. So some important information we may need to encrypt, and while utilizing that information, we may need to decrypt all those informations. So for that, we need support of cryptography engineers as well as cybersecurity engineers. So these are all the roles of some VLSI engineers with specialist knowledge in cybersecurity as well as cryptography. And another very, very important and informative technology is neuromorphic computing. So, we all already might have heard about neural link, right? Brain chip. So this neuromorphic computing, which replicates the human brain's behavior into a chip. So once that chip is manufactured, as a verification engineer, we need to verify whether all the functionalities with respect to whether it is replicating all the brain functionality or not. So based on the requirement given from the customer side. So this is another very important technologies. These are all the important technologies which is there in the VLSI market. So once you have the knowledge on any of these technologies and with some basic idea, so they can able to pitch into VLSI industry. So now I will go more deeper to verification strategies. So these 6 points we will be discussing on what are all the roles as a verification engineer when a particular product is developed as an RTL. When the RTL code is ready, so what are all the steps available to verify those design, and what are all the roles of each engineer. So here one role require different involvement of different engineers. First one is simulation based verification, where we require functional verification engineers. So once the vendor getting some requirements from the customer to develop a chip, so what the RTL engineer will design the code using Verilog or VHDL. So once the code is ready, the next step is of simulation-based verification. Here, uh, the role of DV comes to play, design verification engineer. So what we will do is, as a design verification engineer, so we will get the complete RTL code, and we will be having some simulation tool. For that, we need to develop some test bench, and we need to apply stimulus based on the requirement. So, and we need to verify whether the design is functionally satisfying all the requirement or not. Then there comes the formal verification engineer, they call FV. So here the complete verification environment completely on mathematical based environment. Here the environment will be created in such a way that so we will be verifying the design mathematically, and we will create some proof of concept to elaborate how the design is matching for the requirement. Using mathematically, the complete verification will be happening. The next one is emulation and hardware acceleration. So in the emulation, what they will do, they will use some hardware emulator to mimic the behavior of exact hardware. And in the hardware acceleration, this is completely require FPGA engineers, effort of FPGA engineers. So they will dump the entire binary code into an FPGA to verify whether it is matching the requirement and whether it is compatible for the hardware development or not. Next one is assertion-based verification. So it is also a part of design verification, where we will be having a separate assertion languages, where we will be checking all the signal level aspect of the design. So next one is coverage driven verification. Here also the role of design verification engineer come into picture. So we will be having two different kind of coverage driven verification. One is functional coverage. Second one is code coverage. So in functional coverage, we will be checking whether all the functionalities developed by the RTL engineer, whether he has covered all the functionalities based on the requirement or not. Second one is code coverage. Code coverage. So once the Verilog code is ready, so we need to verify whether all the aspect of code is covered or not. So once this code coverage is done, so we can able to check any of the code is uncovered where we can have potential bugs available. So in that way, functional coverage and code coverage can tell whether we have covered the entire functionality as well as all the codes. So once the code coverage and functional coverage have done 100%, then only we will sign off the RTL. Once the RTL is finalized, we can go for post-silicon validation, where we require that placement and routing engineers, physical design engineers, all the roles will come in the post-silicon validation. And once all the things are done, we can develop the final file which can able to send to the foundry for the chip manufacturing. When the first silicon comes, so all these engineers will support to verify whether the the first silicon is having all the intended functionality which is requested by the customer is meeting or not. Once it is done, so it will be, we call it as tape out. In the tape out only, we will be developing the first chip. So I will walk you through an ASIC design flow where what is the role of functional verification engineer. So in the previous slide, we have seen all the engineers which require for from the RTL design to finally the chip. What are all the involvement of all the engineers? So here I will mainly focus on the functional verification engine. So as I already told, when the design specification we received from the vendor, when the vendor received the design specifications from the customer, so the first job is of the SOC architect. So he will prepare the architecture. When the architecture is ready, the RTL designer will give the HDL code using Verilog or VHDL. Then comes the function role of functional verification engineer. So these three steps comes in the front end. So all other engineering role, what I specified in the previous slide, all come under backend. Whether the emulation, FPGA engineers, the physical design engineer, all will come in the backend role. The RTL designer, SOC architect, and functional verification engineer all come under front-end design. So once the RTL code is ready, so here one thing we need to understand is when a design specification is given, for example, it may have 100 features. So we need to completely develop the chip with including all these 100 features. But at a time, the RTL designer cannot develop the code for all the 100 features. What he will do is he will develop first some 50 features and give it for functional verification. So functional verification engineer will take this 50 feature and he will develop the test bench to verify whether all these 50 features are per the design specification requirement or not. So once he found some violation in the design based on the design spec, so he will send the feedback to the RTL design engineer so that, for example, out of the 50 feature, only 30 features are working. So 20 features are having some bug in it. So he need to report to the RTL design engineer. So RTL design engineer will check all the 20 features and he will do a fix on it, and he will release the second version of the RTL code. All these fixes, along with that, he might have developed some additional 25 features. So he will be giving the second release with some 75 features. With all these 20 feature fix also. So functional verification engineer, we need to check all these. Already we might have developed all the tests for these 50 features. Along with that, we need to verify the remaining 25 features. So again, this loop will be going. So if any feedback, we need to give it back to the RTL design engineer. Finally, when all the 100 features are verified in the functional verification level, we will be going for assertions as we seen in the previous slide, as well as coverage. where we will be checking functional coverage as well as code coverage, right? So these two things will be checked. Once we reach all the 100% coverage, where we will be checking whether all the functionalities are covered in the RTL design, as well as we will be checking whether, for example, he might be giving some 100 files to verify. In the 100 files, so we may have some 1 lakh piece of code lines, whether we have exercised all the 1 lakh lines or not. That only we will be checking in the code coverage, whether all the code done by the RTL designer is exercised or not. So these things will be covered in the code coverage. Once the 100% coverage is achieved, then only it will move to the next level of the verification. So finally, for today's session, so I will be give a brief on what are all the things to be learned to become a verification engineer. First one, as a educational background, all the electronics engineers as well as computer science engineers uh, can become part of VLSI verification. Uh, and the second most requirement is digital design. So one who are familiar with combinational circuit design, sequential circuit design, FSM, finite state machine based design, more machines, milling machines. All these things are prerequisites for the VLSI verification. So in every verification, we need to have the complete knowledge on how a combinational block look like, how a sequential block look like. So for example, we may have some flip-flop design in our design, we may need to verify. So we need to, if we want to verify that particular design of a flip-flop, we need to have the complete functional knowledge on that particular thing. Then only we can able to verify. And FSM. So finite state machines are very, very important in case of VLSI verification. The knowledge on VLSI design. So we need to have thorough understanding on CMOS technologies, Verilog code, because the complete RTL will be in the Verilog language or VHDL language. So if you don't know Verilog code, we can't able to debug on it. And familiarity with some verification tools. So I will give some EDA tools which is free in the market, so we can able to utilize it. So verification tools like Synopsys, Cadence. So those tools will support if you have some basic idea on those verification tools. And scripting languages. So everywhere we know that automation plays a vital role. So in VLSI verification also, we may require some automation. So some set of things we may do recursively. So in order to avoid that, we may require scripting languages like Python or Perl. So if you have the knowledge in these scripting knowledge, it will be an added advantage. So understanding verification methodologies. So verification methodologies like UVM, Universal Verification Methodology, OVM, Open Verification Methodology. So the latest one is UVM verification methodology. But in some companies like Intel, they will use both OVM as well as UVM methodologies. And simulation as well as debugging skill. So with respect to the waveform simulation as well as debugging, so the more practice we may get in from the laboratories, so those skills we need to utilize here efficiently. Then as I told, the coverage driven verification, it is a part of design verification. So as well as assertion, so the separate language is there. For that, we need to know system Verilog. So here system Verilog, OOPS concept will come along with Verilog. So whatever OOPS concept we see in Java, C++, like polymorphism, abstraction, and uh, some task functions we use in C languages, right? So all those things we will be using. So C is a very basic language requirement for learning Verilog. And system Verilog, we require all the OOPS concept. In communication and collaboration. So the communication skill is very, very important because in every day we need to, as a design verification engineer, we may need to interact with the architect team, we may need to interact with the design team, and we may need to interact with the other design verification team, so that we need to efficiently verify the entire design. So for that, the communication skill is very important. Then, of course, problem solving ability and continuous learning. So whenever we move from one project to another, the complete specification will be given to us. So it may be some 300 or 400 page of document. So we need to thoroughly understand of the specification of that particular chip, what is intended for. Based on that, we need to come up with the test plan. So once we understand the complete specification, then only we can able to come up with the test plan, how we are going to verify that particular chip. For that, the continuous learning is very, very important in this field. And so I may show some open source things which can, 1 minute. I'm checking how to erase. So these open sources are very important, and it will be helpful for learning Verilog, system Verilog, as well as UVM. So one is Chip Verify, Verification Guide, and Verification Academy. These are all the website where we can able to learn Verilog language, system Verilog language, as well as UVM, that verification methodology, what I mentioned in the point number 6. And this is the website where we can able to get free EDA tool, edaplayground.com, where we will be having option for choosing the different compiler, Altera compilers, Aldec compilers, Synopsys compilers, Cadence compilers. So we can able to use it for free. If you create an account using our personal email, then we can able to use Aldec compiler. So if you want to use sophisticated Synopsys compiler or Cadence compiler, our official website will be, official email ID will be helpful. So every students will be having an official account with the college, right? With that, if you log in, so you may get the privilege to access Synopsys compiler as well as Cadence compilers in this video playground. So with this EDA playground tool, you can create seamlessly the same verification environment what we develop in company also. So we will be having a separate window for RTL design. If you want to practice as an RTL design engineer, so you have a specific window available in the EDA playground. And for that particular RTL design, if you want to develop a sophisticated verification environment, that also this tool will support. So based on the agenda, I walked you through all the things. From the beginning, we have seen the history of VLSI and what is the job roles as a VLSI engineer, which is there in the market. What are all the opportunities as a verification engineer, and what are all the new prevailing technologies which dominates the VLSI industry, and what are all the technology you need to have some basic understanding. So you can surf on these technologies. and what are all the verification strategies. So mainly I covered the simulation-based verification. And these are all the requirements to become a verification engineer. So these are all, these websites are helpful for self-learning. So, and they will be having some example codes, and this is directly integrated with the EDA playground. So if you refer any code in chip verification or verification guide, so this is directly integrated with EDA playground. So whatever example they're given in this website, you can directly open in EDA playground. All the hyperlinks are provided in these websites itself. I think I'm done for today's topic. So if any queries, or
Thank you, sir.
thank
Audience,
you.
any queries you can welcome to ask, sir.
Or I think this session is already live, relayed in YouTube.
Yes, sir.
So if anyone having some doubts afterwards, also you can put it in the chat. So I'm happy to reply there also.
Okay, sir. So any queries, you can post it in the chat box. Or else, as sir told, you can also ask him later. Okay, sir. Uh,
Okay,
uh,
thank you, thank you.
yes, sir. Thank you very much for a very informative and valuable session, sir. You have given us insights on the job roles for a VLSI engineer and different verification strategies, which would really be an eye-opening for the students to choose and opt a career in VLSI technology, and also for the faculties to pursue their research in the VLSI technology. This session also stressed the importance for all of us to focus and adapt on interdisciplinary approach with the AI and ML, quantum computing, edge computing, IP security, and its role in VLSI. Further, I would like to extend my gratitude on behalf of RMK CET for this noteworthy session, sir. Thank you very much
Thank you.
for sharing this 1 hour for us on a Sunday, sir. Thank you. Thank you very much, sir.
Thank you. Thank you. Thank you. Thank you.